We now come to the vibrations, harmonic forcing of damped systems. So the system contains a damping term as the one we see over here. Therefore, there is a energy dissipating term, which is the Cx dot term. Our f of t is again the harmonic force. It can take the form of a sine function, cosine function, which is more or less the same function, or you might write it, the most general form of a harmonic function is e to the j omega t, where j is the square root of -1, the imaginary number. Now, the response of such a system is again going to be some of the homogeneous solution plus the particular solution. But since this system is damped, the homogeneous solution is going to go to zero rather quickly. So what will remain as a result is the particular solution. So in most of the solutions, we will only consider the particular solution only because the homogeneous solution is going to die out quite quickly. We have three possible cases in which we will be studying the motion. One is the direct forcing, in which the forcing will be directly acting on the mass. We will study it in this video. And then there is the rotating unbalance, in which there is a unbalanced term that rotates like in the washing machine and causes vibrations that rotates with a certain frequency. And thirdly, there is the moving base, such as the base motion. The base is moving with a harmonic force or harmonic motion, and it causes vibrations on the mass. This might be, for example, a model for a motion of a car or a motorcycle or something like that. All three cases have similar but different solutions. So we will study them one by one. And the first one we will be studying will be the direct forcing, in which case we have a force, harmonic force, directly acts on the mass that is vibrating. Also, there is elasticity and damping in the system. We write the equation of motion. We non-dimensionalize it as before. We have the zeta and omega n terms defined as before. And then the particular solution can be written again with an amplitude x, capital X, and it's of the same frequency omega t with the forcing, but now it includes a phase shift of, as you see, phi over here. There's a phase shift of phi compared to the original forcing function. Now, for the sake of solution, we know that this function and this function, these two functions, addition of sines and cosines with a certain amplitudes, as and bs, and this function are the same. We know that from undamped vibrations. And the equivalence is shown by x is equal to as squared plus bs squared, phi is equal to tangent inverse bs over as. Writing the function in the following form, in this form, makes the solution kind of easier to show. And we will do that. We will just take that particular solution like this and try to find as and bs, from which it's easy to convert to capital X amplitude and the phase angle. So we take the first derivative of the given particular solution, second derivative of it, okay, and then substitute it into our original equation, from which you will get some complicated function, kind of complicated, with a cosine omega t term and a sine omega t term. It will be equal to 0. Now, Since cosine omega t and sine omega t cannot be 0 for all times, the terms inside the parentheses need to be zeros. Okay? So this term has to be a 0. The second term has to be a 0, which gives us two different equations. And two equations, as you see, I have written them down here. Let me see. This is the first equation. This is the second equation. They can be written in the matrix form as follows, from which you can solve for A and B, and F0 is the force per unit mass again. And if you do that, it's doable using Kramer's rule or something. You can solve for A and B, or AS and BS, which gives you rather complicated functions of frequency. Okay? But A and B can be solved for. And if you substitute that into your, well, let's go here. And we know that from here, we have solved for, we can solve for x is equal to square root of as squared plus bs squared as before. And phi is equal to tangent inverse of bs over as, I think. Okay, from which you can solve for x and phi. I skipped the intermediate steps, but if you solve for them, you are going to get the amplitude of the vibration of the system is going to be f0 divided by square root of omega n squared minus omega squared squared plus 2 zeta omega n omega squared. Okay, this is the amplitude, this whole thing, times cosine omega t, and then the phase angle, which is tangent inverse this thing. Okay? So we have the particular solution. This is the particular solution. We also have a homogeneous solution, which contains an exponential decay term. So the total solution is the addition of both solutions, but the homogeneous solution, as you see over here, dies out over the time, whereas the particular solution keeps its amplitude for all times. It doesn't die out. The total solution, the effect of the homogeneous solution eventually dies out, decreases, and what we are left after a time instant is only the particular solution. So we will be considering mostly the particular solution and not the homogeneous one. So the magnitude of our response, as you remember, we had x of t, the particular solution was capital X cosine omega t minus phi. Okay? The amplitude or the magnitude of the solution is given by the following function, f0 divided by square root something. Now we can non-dimensionalize this by defining the frequency ratio. We define R to be the ratio of forcing frequency to the natural frequency, and we will call it R, the frequency ratio. If you do that and divide both the numerator and the denominator by omega n, let's say, in this case, nothing will change, but your equations is going to get rather simplified. And what you are going to get will be, well, x divided by, well, your equations are going to be non-dimensional in the first place. So you are going to get, this term is going to be 1 minus r squared squared, because you are dividing everything by omega n here. So it becomes 1 minus r squared squared plus 2 zeta r squared again. The left-hand side of your equation is also non-dimensionalized now because it becomes, when you divide this thing by f0 and multiply it by omega n squared, you will get omega n squared, as you know, is k over m. So x times omega n squared is k over m divided by f0 is, as you know, is something like x times k divided by f0 times m. But f0 was, as you remember, capital F0. So it is xk divided by capital F0. And the phase angle can also be non-dimensionalized by dividing both the numerator and the denominator by omega n. And what you get will be 2 zeta r divided by 1 over r squared. So what I want to emphasize is that f0 over k is called the static deflection most of the time. f0 over capital K is delta static. Okay, that's what we call it. And the x divided by delta static, which is x0 k over x times k over f0, is the so-called magnification factor, which is equal to this thing, 1 divided by square root of 1 minus r squared plus 2 zeta r squared. But you'd better learn this well, because we will be using this very, very often in this course. 1 over square root of, let me write it by hand also, squared plus 2 zeta r squared. Okay, we will be using this, and this thing can be plotted with respect to r, and this is what we get if as a result of this plot. And the plot, we plot different values of the magnification factor, which is x divided by delta static, which we call the amplitude ratio, non-dimensionalized amplitude ratio. For different values of zeta, we get different curves. For example, for zeta equals 0.1, you get a curve that goes to a large value for the r equals 1. As a matter of fact, for damping value of 0, for no damping, the frequency ratio goes to, when frequency ratio is equal to 1, when r is equal to 1, the amplitude goes to infinity because they will have resonance there. At that frequency, the amplitude of the system goes to infinity. For higher damping values, the amplitude values for certain frequencies, they are not infinite, but they become rather large. Because of the damping, those values are not infinite any longer, but they are large. And as the damping increases, the peak amplitude of the system decreases. This is the frequency response, by the way. Don't mix it up with the amplitude of the time response. The amplitude of the time response is shown here in non-dimensional form. Okay, and as the damping increases, the curves become flatter and flatter. And as you see, as the frequency ratio increases, the amplitude ratio becomes 0. All the curves start from 1 and all the curves go to 0. And this is the phase angle. Phase angle always starts from 0 for r equals 0. And it goes to r equals 180 degrees for large values of r. And interestingly, for 90 degrees, for r equals 1, for all values of zeta, the phase angle is 90 degrees. So the system is undamped when zeta is 0. In general, if the value of damping zeta increases, the amplitude of the vibration will decrease. Okay, this is correct for any value of R. For the case of R equals 0, let's look at the previous page. Here, when the case of steady state, when R is equal to 0, all values of M, the magnification, is equal to 1 for all values of zeta. Okay? And for all values of zeta, eventually the magnification goes to 0 when the frequency ratio becomes larger, when the forcing frequency becomes much larger than the natural frequency of the system. Again, for the phase angle, for 0 damping, if the damping is 0, the curve is, this is a strange curve. It is 0 up to R equals 1, and it suddenly jumps to 180 degrees. For any value of zeta, if R is between 0 and 1, the phase angle is between 0 and 90 degrees. And if R is greater than 1, the phase angle is between 90 to 180 degrees. And for R equals 1, the damping value is always 90 degrees. And for large values of R, the phase angle approaches 180 degrees. Okay. One more thing, the maximum amplitude. You see that in this curve, there is a maximum value of the amplitude. You can notice this. Here, for example, there is a maximum value. For each value of zeta, there is a maximum amplitude. And this is the X value, the magnification factor, as we have written down. I have written down it in a different form. Well, if we take the derivative of this with respect to R, we can find the value at which the amplitude of X is equal to 0. So we can take d capital X by dr and set it to 0, gives, let's say, R max, from which X max equals X of, let's say, R max. So the peak values of X for a certain value is called the resonance frequency, the resonance value of the amplitude. Since there is damping, the resonance value is not equal to infinity anymore because the damping dissipates energy. But the amplitude of the resonance is equal to, let's say, X of when omega resonance. And the omega resonance, by the way, is not equal to omega n for the damped case. The resonance frequency for a damped system is not equal to the natural frequency. For small values of damping, it is close to the natural frequency, but it differs to a certain amount, by a certain amount. You can say that the resonant frequency for a damped system, omega resonance, is approximately equal to the natural frequency if zeta is small. You would say how small? For example, if zeta is less than 0.3 or something. 0.3 would be a good number for a small zeta. Okay, this concludes this video.